This is Pawn 0 to Hero. It's the 6th episode of the series, and in the last video I gave all of you some homework. Time to see how you got on with it. If you haven't already tried to solve these challenges by yourself, then be sure to try them first. The link to the GitHub repository can be found in the description. All of these challenges are from great communities, events, or people, so a huge thank you to Seesaw, PicoCTF, and HeliThumper for creating these. But now it's time to jump into the first challenge, a tour of x86. A tour of x86 was created for the Seesaw CTF. I highly suggest checking Seesaw out. They host great events and they have some amazing challenges. But in this one focused towards beginners, we are given a text file containing assembly. This file also contains a bunch of comments which explain everything that is going on, so definitely read through all of that on your own. There are also some questions about this assembly code, and let's start with the first one. What is the value of DH after line 129 executes? Well, this line contains an XOR of DH with DH. Now, what is an XOR? Well, an XOR is a bitwise operation, also known as an exclusive OR. For 2 bits, if they are different, then the result will be a 1, and if they are equal, then the result will be a 0. This Venn diagram should also help you with your understanding of an XOR. In our case, we're doing an XOR where the 2 arguments are the same. This means that the result will be a 0, since if you XOR something by itself, you get a 0. First question out of the way. It's as easy as that. Let's move on to question 2 then. Question 2 is, what is the value of GS after line 145 executes? Looking at that line, we see that it contains a move GS dx, meaning move the value of dx into GS. Thus, after that line, GS will contain the value of dx. Now we just need to track our steps through the binary to see where the value of dx gets set or changed. And we see this happen in line 131 and 132. Here, dx is set to the value OXFFFF, by this move operation, and then the bitwise NOT operation is ran on that value. The easiest way to get the result here is to write out OXFFFF in bits, which is just 16 ones. Then we can do a NOT operation on each one, turning it into a 0, which just leaves 16 zeros, which is just 0. So the value of GS after line 145 is 0. I hope you were able to figure that one out. If not, don't worry, let's move on to question 3. What is the value of SI after line 151 executes? That line contains a move SI SP. Okay. We need to figure out the value of SP. Backtracking, we find move SP CX at line 149, so we need to find the value of CX. And finally, at line 107, we find a move CX 0, thus moving 0 into CX, and that answers question 3. 0 is the value of SI after line 151 executes. Time to increase the difficulty level a little bit with question 4. What is the value of AX after line 169 executes? Well, line 169 is a move AH OX OE, thus moving the value OE into AH. But the question is what the value of AX is after that line. Now, do you guys still remember the very first episode of this series where we talked about registers, RBP, RAX, and so on? Well, we also talked about EAX, which are the lower 32 bits of RAX. Then we also covered AX, which are the lower 16 bits of EAX. We can then split AX further up into AH and AL. Now, AH is something we didn't discuss in the first video because it's rarely ever used. However, knowing about RAX, EAX, and AX should give you enough knowledge to efficiently search for what AH could mean. This course will try to give you the tools to do amazing stuff, but we can't go into every single little thing, so always be prepared to do a little research on your own, because that is what hacking is all about. But okay, knowing that AX is made out of AH followed by AL, that means that line 169 already gives us the first byte of AX. Now we just need to find the byte that AL contains. And that's just one line above here. We see that T is being moved into AL. Now T in bytes is just 0x74, so the value of AX after that line executes is 0x0e74. Are you still with me? I hope so, because I have one more question to discuss. What is the value of AX after line 199 executes for the first time? That line contains a move AH OXOE again. Thus, we get the first part of AX for free. Now we need to figure out what AL will be, and the line before this one gives something away. Move AL square brackets SI. This means we're moving the value that SI points towards into AL. But where does SI get its value from? Well, in line 189, it gets it from AX. And then AX gets its value in line 180, where .string to print is moved into AX. Now, what is .string to print? It's a label, and 2 lines below that we can see how the label gets its value. The DB instruction is used here, and the DB statement initializes memory with the byte value, and the label will then be assigned the memory address of the first byte value. So pretty much we're just putting this ACOS new line by ELK in memory and getting the address. So that address is moved into AX, then into SI, and that is what SI holds. Now here we also see that the value of SI is being compared with 0, and if that's the case, then we jump to .end. And down here we see that SI is being incremented. We are in a loop, looping over this string. But back to the question, what value will AX hold the first time this loop is executed? Well, AH will be our OXOE, and then AL will be the first byte of our string, which is an A or an OX61 in hex. Thus, the last answer of this challenge is that AX holds OXOE61 after the loop has been executed for the first time. And that's this first challenge. The last one here was quite difficult, but I hope that you now have the tools to kind of look into it yourself if you didn't quite fully understand it yet. I also hope that you were able to solve at least 3 questions here. That would be a great start. Let me know in the comments if you managed to solve that many. But for now, let's move on to the next challenge. Right now, we're gonna talk about the strings challenge, and this is a challenge that was originally used in the Pico CTF in 2018. Now, Pico CTF is a great CTF for beginners, so definitely check out their websites, their competitions, and the challenges that they have up and running constantly. In this challenge, all we got is a binary, and this binary is called strings, and if we execute it, so /strings, then it says, have you ever used the strings function? Check out the man pages. Okay, so this seems to point towards a strings function, strings command that we should use. But before we do that, let's go into Ghidra and check out what is actually happening in this binary. Maybe there's something hiding. So over in Ghidra, I can see all the functions here. And really only the main function is interesting here. And well, it doesn't really do much. It just outputs that text to the screen, which we saw happen. This binary does not really have much to hide. I mean, it's doing exactly what the code says it will do. Well, let's run strings on this binary, like the binary wants, and let's see what happens. So I'm gonna run strings on our binary, which is also called strings. And now we see that we get a lot of output. And when I mean a lot of output, we see a ton of it. And we can scroll all the way up here, we see a bunch of these weird, seemingly base64s something strings. And that is very odd and peculiar because, well, in the code of our binary, we didn't really see anything. In these functions, there are just the basic functions and then your main function. And all of this data is not represented in the binary. And well, the main lesson of this challenge is that binaries don't just consist of the assembly code. There are a bunch more parts that make up a binary, and here above in the program trees section of Ghidra, we can see that. Because here we can see all of the other sections there are. The code is just the .text section, which is your executable text or your assembly code. But there are all of these other sections that also contain some data in some cases. You don't need to know about all of these and what all of these do. There are a bunch that we'll cover further on in this series, such as the GOT, the global offset table, the PLT, and so on. We'll cover all of those later. But right now, the ones that I want you to know about are the .data section and the .read-only data section. So data and .row data. Now, .row data is the read-only data section, which is a section in the binary used to store data that can only be read. Then we have the data section, and that is a section in the binary used to store data, and this section can be written to and read from. So in the read-only data section, we see our string. Have you ever used the strings function? That we see outputted. But in the data section, we see that it's incredibly long. There is a lot of stuff in here. And if I scroll through there and stop it at certain points, you will see some of these weird strings that we also saw when running the strings command. What is going on here? So all of this is contained within the binary. It's not used when running it, but it's still in there. And somewhere along there will be a flag, which is the goal of this challenge. Back to the strings command, because we just saw all of that in Ghidra, but what does the strings command actually do? Well, the strings command is very, very simple. It will just take the bytes of anything you feed it. So anything, it doesn't have to be a binary. It will take those bytes and it will find sequences of 4 or more bytes that represent valid characters. So printable characters, things that your terminal knows how to display out to the user. Printable characters are things like your letters, your numbers, semicolons, all of that kind of stuff. If it finds such a sequence, it will just print it out to the screen. So the strings command here has no awareness at all of this being a binary. It doesn't care about sections and whatnot. So it's kind of the dumb approach to finding text in a binary. That doesn't mean it isn't a good approach. It's a great thing to do when looking at a binary, so I highly suggest always running it and just seeing what kind of strings you can find, because that can already quickly disclose some secrets that the binary may hold. But in this case, we haven't found the flag yet in our binary, and we need to do that. So now there are a couple of things here that you can do. You can just manually scroll through all of these, finding something interesting, and that will take a long time. However, in the CTF, we know that there is a set flag format, and that's a format that the flag will hold. And in this case, that is just pico CTF. So if we just run our strings command, but grep for the string pico, and then run it again, we see that we get the flag pico CTF strings saves time. Now the strings command is really amazing. Definitely check out the man page of the strings command, because you can do stuff like changing the minimum length required when running it. So right now it's looking for 4 bytes or more, but you can change that to 5, 6, 7 bytes. You can pick encodings. You can change a bunch of options here that might make it easier for you. So definitely play around with all that. But that was this challenge. A pretty easy one that I hoped you were able to get some progress in. If not, that's alright. But for now, let's move on to the next one, which will step it up a little bit. Welcome to the salty Spitoon. How tough are you? Well, I'm pretty tough. Yeah, right. Back to Weenie Hut Jr. with ya. Seems like the goal of this challenge is to become tougher. Let's show this challenge by HeliThumper just how tough a hacker can be. I've opened up the challenge in Ghidra and decompiled the main function, and it looks like this. It starts with a calloc, which will allocate some space on the heap, and then it will output dat 00102 and so on. And by double clicking that, we can see that it prints out the welcome to the salty Spitoon text. Next up, we have a scanf of %s into the allocated memory, and then a call is made to a validate function with our input as an argument. And that is quite interesting. And it becomes even more interesting because if the return value of that validate function is equal to a 0, then it will output, yeah right, back to Weenie's hut. And if not, then it will say right this way. Thus our goal is to make that validate function return something other than 0. Time to look into it. The validate function is a bit more complex. It starts off with assigning seemingly random values to a lot of variables, and then it takes a string length of the first parameter or input. Now it's doing a do while true loop, and at the end of that, local 50 is being incremented. So this is just a loop and local 50 is I. So let's rename some variables here so we have everything make more sense. In this loop, it will check if the length of our string is smaller or equal than I. If so, then it will return 1, which we want. Aha, so we're looping over our input. And if it's able to fully loop over our input, then we succeed. But what's all this mess here? Well, that's a canary. Don't worry about this for now, it'll come up later in the series. But after all of that, we have another if statement. This one will check the ith value of our input and compare it to the ith value of local 48. Now, local 48 seems to contain only 4 values, so is the answer only 4 characters long? Not really. See, all those other variables here, all of them occur on the stack after our local 48. So if I is equal to 5 here, then it will just take one of those values. Now, if our input is not the same as that value, then we will return 0. Easy peasy, we just need to pass in the correct values. I like doing this kind of stuff in Python, and here I've made a list of all of the values from the binary, so just the values of the variables, and now I can very easily turn them into characters by using CHR, and I do that in a list to get the string values, and then I'm going to use a join to join that list together so that we have a nice string, and this looks quite correct. So let's try it out, and we see that it works. Great. Challenge solved. Now, as a little bonus, some of you may have noticed a small oversight by the creator of this challenge. In the binary, there is no check for the length of our input. Thus, we can also just pass in a single character, such as the first F of the correct answer, and the binary will just still accept that. So did you spot that one? Well, because small things like that can become very important when dealing with complex exploits, so very well done if you did. For now, let's move on to the next and final challenge of this episode. Let's get into the last and hardest challenge of today. But don't worry, just believe in yourself. Get it? Because the challenge is called Beleaf. Anyways, when we run the binary, it straight up asks us to enter the flag, and upon entering something, we see that it's incorrect. Okay, we need to find the flag, and this can't be too hard, right? Well, let's open up the binary in Ghidra, and immediately we see that our function list looks strange. What is this fun underscore doing here? Where is my main function? Running file on the binary and seeing that it is stripped explains a lot. Binaries are often stripped to reduce the file size, since stripping removes all the names for symbols such as function names. In this case, we need to manually figure out which function is the main one, but luckily there aren't too many, and seeing that this one prints out enter the flag makes it pretty clear. Now, the decompiled C code here looks pretty unintelligible, so when solving challenges like this, always try to rename stuff so that you can put all the puzzle pieces together. I'm going to just skip to the point where I've done that, as else these videos would be a little too long for you. Okay, this is what the code looks like. After we pass in the flag, it's going to check if the length of our input is 0x21 or 33 bytes or longer. If not, then it's going to say incorrect. Thus the flag is 33 bytes or longer, and then it's going to enter a for loop, which is clearly looping over our input. In there, it's going to run this function on each character, and I've named it the transform function since it will transform our character. Now we get to an if statement, where our transformed character is checked against some data stored in the binary. Looking at that data structure, we see that it contains 1 byte of data every 8 bytes. Now, if our transformed byte doesn't equal the byte from this data structure, then the program exits. Thus, we need to make sure that they're equal, hence why I've called this the desired output. So all we need to do is figure out how this transform function changes our input and then reverse it. Let's go! Again, I've cleaned this function up by renaming a bunch of stuff. Okay, so this function is going to loop over another data structure until it has found our input byte in that other data structure. Then it's going to return I. Now in the loop, it's going to check if our input is smaller than a value from the data structure, and then it's going to modify I in some way. But if that's not the case, then it's going to modify I in a different way. That sounds very tricky and just very hard to reverse. What if there was a way to not have to reverse all of this? And this is something you should always keep in mind when looking through a binary. So far, we spent a lot of time on understanding every little detail, but very often you don't have the time for that. So there are ways to get around that. And I'm going to show you two ways, a dumb one and a smart one. But first, the dumb one. We see that no data is ever being changed here. It's just taking a value, doing some calculations, and returning a value. So if we run this function 100 times for the input A, then the return value would always be the same for that same letter A. Now, our input is a value between 0 and 256. Thus, there are 256 options. My mind immediately goes to brute forcing. We can try to run this function for every single byte and then just create a lookup table for the output. If that doesn't make sense, then let's just do it. So I've pretty much copied the transform function from Ghidra and made some modifications here in a C file. The modifications made to make it run are that I've made the lookup table a character array with the values from memory. I used this little terribly overcomplicated piece of Python code to extract the values from a text copy of Ghidra. It's terrible, but never mind that. I now just have these values in the lookup table character array. Another thing that I changed was that I added in this if statements that make sure that we don't end up crashing, because I kept on getting increased and it just messed everything up. But besides that, the function is the same. Now in the main function, I have created a for loop that loops over all possible bytes. Then in the loop, I run the transform function, and if the result exists, I print it out. Now let's run this, and we see a bunch of values here. Now these are the outputs of every single possible character, and then what number that character generates if we run it through the transform function. So now we can just check the desired output in the binary and look up which character it matches with. The first one is a 1, and in my lookup table I see that that's an F. Then we have a 9, which is an L. Then an OX11, which is an A, then OX27, which is G, then OX02, which is just an open curly brace, and that's the flag format. Thus, if we continue, we have the flag. Great. Now, that was the dumb way of doing it. It was a lot of work that is pretty much pointless because our transform function will return I. But when will it return I? Well, only if the character we passed into the function is equal to the ith character in our lookup array. Therefore, if I want to know what character would cause this function to return 1, then I just have to get the first character from the lookup array, which is F. If I now want to find the value that causes this function to return 9, then I just have to find the 9th character in the lookup array, and then I can find the OX11th, the OX27th, and every other number in our desired output. Doing that will also get us the flag. Now I'm not going to go through all of them here in the video since that would take way too long, but the flag that we would find this way is flag we believe in your RE future, which when fed to the program, it returns correct. And that is the smart way of solving this challenge, by just thinking a little out of the box. So although there are multiple ways of solving this, there clearly is a better or easier one. Getting a feel for all of this requires experience, and you get experience from just doing these challenges. Solve CrackMe's in CTFs and you will get that feeling. But believe me, very often I still spend hours doing something just for somebody to come along and say, hey, you could have done that way faster this way. And that is just how it goes. So don't worry at all. And that wraps up our first homework video. I hope you enjoyed watching through these yourself, and I hope that by watching me solve them, you've learned some new bits and bobs here and there. Now, if you did, definitely let me know in the comments. Is something not quite clear yet, which is possible, then let me know as well. But that marks the end of today's video. In the next one, we are finally going to get into Stack Overflows, so definitely look out for that one. And if you don't want to miss it, then be sure to subscribe to the channel. Click the like button if you liked the video and be sure to comment any questions, concerns, or just nice things below. But that is it for me. I hope you enjoyed the video and I would love to see you back for the next one.